Superstars of slicing with CircuitPython. It's Prof. G, and in our last lesson we learned how to use list slices with Neopixels in CircuitPython. In this lesson we'll use that knowledge to get Neopixels spinning and to create a gauge that you might use for something like volume control. And along the way we'll learn about list comprehensions. Get ready to comprehend the big learning. Now let's begin. Plug in that Circuit Playground board, Blueford or Express, open up PyCharm, and if you're new here, welcome. You might want to check out the course playlist to see how we got to this point. So let's first write code to move the lights around the Circuit Playground, either clockwise or counterclockwise, and we'll get an intro to list comprehensions along the way. So I've got the slices, lists, and NeoPixel code that we finished at the end of the last lesson. Let's reuse the first portion of this code. We can delete everything below the creation of the pixels object. Oops, and we're also going to want a while true below where we have a pass inside to keep the lights on. Then I'm going to write a for loop that lights up each light in a different color from the colors list. So this should be pretty familiar to everybody. If we say for I in range, passing in the length, passing in pixels with a colon at the end, then we can set pixels in brackets I equal to colors in brackets I. Then open the terminal, get into TO, save, and this is what we get. A nice little rainbow all around our Circuit Playground. Well, that's cool, but I want to show you a Python technique known as list comprehensions, and it's really useful for data analysis, but it can also be useful when working with Neopixels. Now, we just wrote this for loop, and it works great, but now let's write it with a list comprehension. List comprehensions are shorthand code for creating a certain type of sequence on a single line instead of using a multi-line for loop. Now, in our case, this is only going to save us one line, but it's good to know about list comprehensions. They can make your code more compact, but if you decide that your code is more readable with the standard for loop, either one does the job. You will see list comprehensions in more advanced sample code, so you really want this in your CircuitPython toolkit. Now note, when I defined list comprehensions, I said certain types of sequences. Not to get into the weeds too much, but the NeoPixel object that we have isn't technically a list. It behaves like lists. After all, we're using list slicing and we're using list comprehensions, but we don't have full access to all of the list features. We can't do things like use the append or remove method. Once a NeoPixel object is created, it has a fixed length, whereas you can change the length of a standard list. I often call NeoPixel objects lists, even though they're technically not full lists. I think it's okay for you to refer to them as lists as long as you know they can't do certain listy things. But here's the scoop on list comprehensions. So list comprehensions always have the code on the right of the equal sign enclosed entirely in square brackets. Forget those square brackets and your list comprehension won't work. There's also a for clause inside, and in this case we're going to iterate through a range from 0 to 9, and we've calculated this using the length function, exactly the same as we did in our old for loop. And just before this for clause, but just after the opening square bracket, is our expression. This is going to determine what we put in each element of our sequence. Again, I think it's okay if you call this a list. This is a list comprehension. So in our case, we're going to put a single color from the colors list each time we go through this for loop. Now in the list comprehension, we don't need to specifically say pixels bracket I equals like we do in this line. The left side of the equation in the list comprehension just has pixels with square brackets and a colon and no value inside. That says apply what we're doing on the right side of the equation to the entire list. It'll update each element of pixels one by one. Now this might look a little strange at first, but just remember, you need square brackets. The first part is the expression that determines your results. For us, that's just to get the ith element of the colors list, followed by the for loop that you iterate through. And there's more stuff we can do in here with things like if clauses and ternary operators. No need to introduce those now, but hopefully after we enter and run this code, you'll understand list comprehensions. So back in PyCharm, I'm going to highlight the two lines of my traditional for loop and command / to comment these lines out. Then we'll write the same code as above, but using a list comprehension, a one-liner. And in here we start with pixels, in square brackets, only a colon, no values, and set this equal to, in square brackets here, all of your list comprehensions have square brackets surrounding them. And our expression, the thing that we want to do to every value in pixels is we want to get colors, bracket I bracket, and then to the right of this we put our for loop in, which is for I in range, in between parentheses, len, in between parentheses, pixels. And you want to use pixels in here and not colors because there are fewer pixels than there are in the colors list. But this for clause here is the same as this for clause up here. Our expression here is the same as what's on the right side of the equation inside the for loop up here. And by saying pixels in between brackets with just a colon inside, in front of the equal sign says take the entire list comprehension, iterate through the elements one by one, then take the expression and put them in each value inside of the pixels list. That's it. Let's save this. The result looks entirely the same, but you did it on one line. That's list comprehensions. And now let's get that rainbow spinning. So we'll get rid of the pass statement because we're about to create some counterclockwise spinning. So here's a look at what we want to accomplish. And sometimes it helps to write things out on paper. I do that a lot, sort of like what I'm representing here on the slide. And this will give you a sense of what you want to do in code and what problems you might run into. So we've got 10 NeoPixels labeled 0 through 9. Here on the circuit playground diagram, you can see that they're labeled counterclockwise, but I've also represented the initial colors, lining them up in a row like this. And to move counterclockwise, we want to move the colors that are in 0 through 8 into spaces 1 through 9. And we want to move what was in 9 into 0. But unfortunately, if we do it in that step, we're going to overwrite 9, so we've lost the value that we wanted to put in 0. But here's what we can do. We can create a temporary variable that we'll call temp_value, and we can put the value in 9 into the temp value before we move the slice. Then we can move the slice from 0 through 8 into slice 1 through 9, and then we can move what was in our temp value into position 0. And to do this, we need 3 lines of code. Temp_value equals pixels 9. That takes what was in 9 and puts it in a variable named temp value. Then we shift the slice from 0 to 8 into positions 1 through 9 with this line of code. But remember, the stop value in the slice is 1 more because we approach but we never reach that value. It can be a little tricky if you forget that. Then we take what was saved in temp_value, the old position 9, and we put that in position 0. So hopefully that's clear. Let's code this up and see it work. We'll first say temp_value equals pixels and in brackets 9. That's to save 9 before we overwrite it. Then in the next line, we'll say pixels and in between brackets 1:10. So that's going to take the slice from 1 to 9. Remember, we never reached 10. And we're going to set that equal to pixels and in brackets 0:9. That's the slice from 0 through 8. So it moves 0 through 8 to 1 to 9. Then we set pixels in bracket 0 equal to temp_value. That moves the temp value into 0, the start of the sequence. Now just to slow things down a little bit, we'll say time.sleep in parentheses 0.1. Then let's open the terminal, make sure you're in TIO. We'll save this. And look at that, you're spinning the rainbow. Nice work, Pythonista. We've leveraged slices by copying one slice into another slice to get spinning happening. So I'm going to change the comment up top to say spin with slices, and I'm going to use this as the name to save this to our CircuitPython school folder, and we can close the outer tab. And now it's time for a challenge. This challenge is A clockwise, B counterclockwise. So you want to modify the spin with slices.py code that we just created, and we'll start out with the NeoPixels lit up in the rainbow pattern using the list comprehension. We already coded this. Don't begin rotation yet though. Then code up the 2 buttons that are built into the circuit playground, and when button A is pressed, rotate counterclockwise. When button B is pressed, rotate clockwise. Save the code as slice spin both directions.py. This is what the code should look like when running. So the rainbow's motionless when the code first starts. Pressing A starts that counterclockwise rotation. Pressing B changes to the clockwise rotation. You should be able to continue to shift rotation by pressing the appropriate button. And you've got what it takes to make this happen. Why don't you give a pause, try this out, and when you're ready, let's resume and we'll compare answers. Now since we're going to work with buttons, we should import digital I/O. And just before the while true loop, we'll set up our buttons. We'll say button_A equals digital IO dot digital in out, capital D, capital I, capital O. And in parentheses, we pass in board dot in all caps button_A. Then we need to switch to input and set the resistor type. So we'll say switch to input. And between parentheses, we pass in digital IO dot capital P pull dot all caps down. Then we can copy these 2 lines, paste them down below, and replace the 3 areas where we refer to button A so that they're button B. Now, there are a lot of ways to set up should we be moving in one direction or another. I'm going to demonstrate a technique similar to other examples we used when working with buttons. So when you press the button, they're just going to set a flag. Should we move in one direction or in the other direction? And when you hear programmers talk about setting a flag, they're just talking about setting a variable that acts as an indicator. Should I do one thing or another thing? Has the state changed from one situation to another situation? And then we're going to use an if statement outside of the button code to see if we should rotate in one direction or another. So we'll name the variable that's going to act as our flag as move, since that will indicate if we should move in one direction or another. We'll initially set this to 0, no motion, but if move equals 1, then we should move counterclockwise. If move is -1, then we should move clockwise. And the number in here actually doesn't mean anything. We're not going to use it in math. It's just a flag. Now we'll write the code to detect the button presses, and those will just set the flags. So if button underscore a dot value colon, then move equals 1, and if button underscore b dot value colon, move equals -1. Make sure your indentations are set properly, so 1 level indented for the 2 if statements, 2 levels for what's inside the if statements. Then if move equals 1, then we're going to perform the same code that we wrote below. So I'm going to say if move equals 1 colon, remember equals means it's the same. This evaluates true or false, and if it's true, I'll highlight these lines and just make sure that they're indented under this if statement. Then I'll outdent and put an elif statement in here. We'll say elif move equals -1 colon. And you're never going to have a situation where one is true and the other is true, so an if elif makes sense here. Your program would still run fine if you used 2 if statements instead, but if elif is a little bit more in keeping with the actual logic of the code. We're not going to use else because there is the possible condition where move equals 0. That's where it is when it starts and there's no rotation. So we don't want to initiate a rotation one way or another if move equals 0. That's why we're using an elif move here instead of just the else. We start with move equals 0, and neither the if statement nor the elif will be true, so we'll keep looping through while true until one of the buttons is pressed. Then the code I write in this condition is going to be opposite what I wrote in the condition above, so I'm going to highlight all of the code under move double equals 1, copy it, then paste it under elif move double equals -1. I'll change the comment. This is for clockwise spinning, and the first statement isn't going to store pixels 9, it's going to store pixel 0, and the third statement down here isn't going to update pixel 0, it's going to update pixels 9. And then we change the middle statement from reading pixels 110 equals pixel 09 to read pixels 0:9 equals pixels 1:10. Now let's open our terminal. TO's running. I'm going to save. Nothing's running when we start. Press A, clockwise rotation. B, counterclockwise rotation. And you can continue to press those different buttons. If you hold your finger down, there's no negative effects. You can even press the restart button and restart your code and start with B instead of A. Everything seems to work fine. So let's change the comment up top to read slice spin both directions, and we'll save this to our CircuitPython school folder, and we'll close that outermost tab. Good work. Next up is the volume gauge challenge, and we'll use this solution in a future lesson where we learn to adjust the actual audio out volume using something called the audio mixer. So in this challenge, we're going to modify the code that you just wrote, start with no NeoPixels lit this time, and when button A is pressed, the pixel should begin lighting at 0 and should continue toward 9 as long as the button is held down. Now I suggest adding a time delay of 0.2 seconds after processing each press detection. That should make sure that too many lights don't turn on for each press. So if you tap quickly, only one light should go on at a time, and the effect should seem like button A is turning a setting, like volume up. You'll see the circuit playground become increasingly red as you press or hold down button A. Then when button B is pressed, we'll do the opposite. Pixels should begin turning off largest number to smallest, so it seems like this turns the volume down. And enough button presses should turn all the lights off to indicate that the volume is at 0. Now note, you could use debouncing buttons to react to one press at a time. Standard buttons will allow you to hold down a button though and repeatedly raise or lower volume, which is probably what somebody would expect from a volume interface. Now use slices to achieve this effect with the Neopixels. Now you can use a list comprehension, but I'm going to show you a better technique with list comprehensions when we cover the solution. And when you're done, save this code as volume, button, display, and the video at the right shows a proper solution. So why don't you pause and give this a shot? You can always go back and take a look at any of the techniques if you need a reminder, and when you're ready, resume, and we'll compare answers. So let's first set the comment up top to read volume-button-display.py, and we're no longer going to light things up in the rainbow pattern, so I'm going to get rid of everything between pixels and where we set up our buttons, and we're no longer going to have a flag called move, so I'll delete that. And I'm going to delete everything inside the while true, except for if we check to see if button A is pressed or button B is pressed. Now here we're not setting a flag, we're actually going to work with volume. So I'm going to create a variable outside of while true called volume, and I'm going to set that equal to 0. Then underneath if button A dot value colon, so if button A is pressed, we're going to check to see if volume less than len, the length of in parentheses pixels, colon, this ensures that we never try to light up a pixel that's 10 or greater. That would give us an error. Remember, we're 0 index, so the first pixel is 0 and the last one's 9. Then for each press, we want to increase the volume. So we could say volume equals volume plus 1, or we could write it with a shorthand, volume plus equals 1. They're both the same. Then we want to light up in red pixels, and in between brackets we'll say 0:volume. Now remember, we go up to volume, but we don't reach it. So this is brilliant, because if the volume is 1, we're only going to light up 0. If the volume is 2, then we're going to light up 0 and 1. If it's 3, all the way up to, if the volume is 10, we're going to light up 0 through 9. And we'll set this equal to red times volume. Again, this lights up 0 to volume minus 1 in red. And so the rest of the light should be black. So we should say pixels, and in between square brackets, volume, because remember we stopped at volume minus 1 above, colon, nothing after the colon. So that'll go right up to the very last pixel in our pixels list. And we'll set this equal to black times, and then we've got to calculate how many black pixels there should be. So between parentheses, we'll say len, the length of in parentheses pixels, and then outside of length, we're going to subtract volume. That gives us whatever's left over that's not red. That'll essentially turn the rest black. Then I'll outdent and we'll say time.sleep, passing in 0.2. Again, that just slows down the reaction so that we don't turn on too many lights when we press the button. Then down below, the first couple of lines are going to be the opposite. So if button B dot value, so if we pressed button B, we're going to say if volume greater than 0, colon. Now this ensures that we never go below 0. Then we want to subtract 1, so volume is going to equal volume minus 1, or we can use the shorthand volume minus equals 1. And then, look at this magic. We want to light up the pixels. We want to light up those slices the same way we did above. So I'm going to highlight these 3 lines from the previous if statement, copy those flexible bad boys, and I'm going to paste them below, and our code is going to work. Let's open that terminal, make sure TO's running. Mine is. We'll save, and let's try this out. Press A. You can hold down the button as well. If you try to press B, you'll see the lights go down. Make sure you can go all the way down to 0 and all your lights turn off. Make sure that when you try to go beyond the last light, light 9 for a volume of 10 lights lit up, that you don't crash the code, that your code still works. So trying out all of these edge cases is a good thing to do. In fact, I'm going to restart my board now by pressing reset. This starts my code executing right from the beginning, so all the lights are off. And instead of pressing A to raise the volume, I'm going to press B just to make sure that there's nothing in my code that's going to crash if I subtract a volume when there's no volume up right from the start. And yep, this is working fine. I can still raise the volume, lower the volume. This is looking good. So hopefully if you take a look at this code, if you struggled with it, it's okay. We just learned about slices, but really pay attention to this. Make sure that you know how this works. Slices for the solution win. Now why don't we go ahead and save this to our CircuitPython School volume. Remember, we named this volume button display, and then close that outer tab. But remember, I said that I was also going to show you how to do this with a list comprehension, and we were going to extend what we know about list comprehensions. So here goes. Now, a reminder of how list comprehensions work. There are 3 parts to them. First, if we want to apply this to the entire list, we give the name of the list, then square brackets with only a colon in between. This means apply to the stuff on the right-hand side of the equation to the entire list. Now remember, the entire list comprehension, the stuff on the right-hand side, is enclosed between square brackets. Then we've got a for loop. This one goes through a range of the length of all of the pixels. That's 10 in our case. We never get to 10, so we go from 0 through 9. Then for each of those values, 0 through 9, we evaluate the argument here on the left-hand side just before the opening square bracket. And for each of the values 0 through 9, we pass the corresponding color 0 through 9 from that colors array that we had previously had in the earlier example. Remember, in the previous lesson, this gave us our rainbow pattern list. Cool. Now to get our pixels to light up as either red or black, we're going to have a list comprehension that looks like this. We still apply the results to all of the pixels, so the left-hand side of the equation is the same, and we have a for loop that'll go through all 10 NeoPixels. Those are, again, 0 through 9, but what's different is the argument, and this one evaluates what to put in each element of the pixels array by using a ternary operator. Remember that guy? That's the one-line if-else statement that we covered a few lessons back. We only used it once, but it's super handy here because we can put this one-line if-else statement inside of our one-line list comprehension into one massive statement, but that does everything with just one line. Now, if you forget how ternary operators work, here's a refresher. This part here evaluates a Boolean condition. It returns true or false. In this case, if I is less than volume. Now, if that's true, what we want to do is on the left-hand side of the Boolean condition, we want to light a pixel in red. So we just pass red over to our NeoPixels array. Otherwise, if it's false, then we set the pixel to black or we turn it off. And if you wonder what the results are like, let's apply this to the button down volume in our code. And you can do the button up volume with button A on your own. So if button B is pressed, the volume goes from 10 to 9 all the way down to 0. So red is going to go through 8, then through 7, then through 6, all the way down, and just 1 is going to be highlighted at the very end, but if we get to volume 0, none of the values are going to be red. And the opposite is going to be true for the lights that we shut off. So we start off at just 9. Now remember, we just pressed B to lower the volume, and if we were at 10, then we're just going to turn off one light. That's why 9 turns black. But then 8 and 9 are black, all the way down to when we're at volume of 1, 1 through 9 are turned off, and then when we get to 0, 0 through 9 are turned off, all the lights are off. So that's it. Let's code this up, and if this isn't clear to you now, try out the code, get things working, then you can return to this portion of the lesson and rewatch things. It might be a little clearer to you then. Let's modify the code that we just wrote, and why don't we change the comment up top to read volume button display list comprehension. Then head into the while true loop, and in the section where we detect if button B is pressed, we're going to get rid of the 2 pixel slices that we have here, and we're going to replace these with a single list comprehension. Now we're going to start this with pixels, and between 2 square brackets, just a colon inside, that's it, and we'll set this equal to, and between square brackets, sometimes it's helpful to build out the list comprehension, thinking about things like from the for loop first, so that's what I'm going to do. I'll say for I in range, and then pass in length, and then pass in pixels. Then to the left of this, but still inside of the square brackets, we have our argument, and that's going to be a ternary operator. I'm going to actually write the conditional statement first. So I'll say if I is less than volume. To the left of this is what we do if it's true. We're just going to pass in red. But then if it's false, to the right of the if conditional, so if I less than volume, we'll say else black. That, my friends, is it. So the structure might seem a little complicated, but if you write it like I wrote it, maybe that's a little bit clearer to you. Open the terminal, everything is running, let's save, and let's try this out. So we'll start out by pressing A, and as we press this or hold down, it's still using slices, so we don't expect to see any changes here. Then let's press B, and we don't expect any changes here either, but this is the one that's using the list comprehension. And this works for single presses, or we can press and hold down, and if we try to go beyond volume 0, it doesn't crash our code, but all of our lights are off as expected. So this is looking good. You can continue to try out button A and button B, but now we've got things working not just with slices, but also with list comprehensions. Nice work. So why don't we save this to our CircuitPython school folder, so you've got this as notes and things that you can refer to later on, and always close that outer tab. Excellent work. So once again, you absolute code legend, we had more big learning. We learned about list comprehensions. We spun NeoPixels counterclockwise and clockwise, performed via a challenge. We created a volume style gauge using NeoPixels, and we created a more complex list comprehension using a ternary operator. I hope you're feeling good about that learning. Let me know if so in the comments. Like, subscribe, and tell your homies, and keep hacking.